All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Wrapping up the spring semester. So we have just today and next week, and then we'll be done. Okay, so today we will be continuing what we discussed started on Tuesday about hypothesis testing. So we're going to get do a few more examples of this. It could be a little bit confusing in terms of just the terminology. So just kind of just I'll try to be as explicit as I can in the examples, but it kind of you kind of have to talk your way through these a few times to really kind of understand what's going on. But we'll do a few examples today so you get used to that. So hopefully we can finish up today, and then Tuesday we'll do our final topic of the class, which is linear regression, which may or may not be a full lecture. Okay, and remember the plan is for next Thursday to be completely a review session. So next Thursday, no new content, just reviewing for the final exam, because our final exam for this class is a little bit early in the week, so it's on Tuesday. I believe it starts at 4 p.m. Or 5 p.m. In this review. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. So I'm just going to scroll up a little bit. You don't have to write this down again. You guys wrote this down last time. But basically, in this section of the of the class here, we are interested in seeing how can we test for the validity of hypotheses. Okay. Now, when you're doing engineering, when you're doing any kind of testing or science, you're going to be making hypotheses, constantly, all the time, whether you really understand it or not. Right. So our definition for a hypothesis in this class is a theory or a guess for the numerical value of a certain quantity. Okay. And the kind of the requirement here is that we have to be able to test for that quantity as well. Okay. So in other words, this should be something that we can verify with experiments. Okay. All right. And so the example that we were going through right before we left on Tuesday was that we are manufacturing a product that requires some structural wire. Okay. Part of our design requires that this wire be able to withstand 200 pounds of force before it breaks. Okay. And so we want to form a test, or we want to form a hypothesis to basically make sure that this is actually the case. Okay. Okay. And so we were kind of in the middle of kind of walking through kind of the step-by-step process through which you can actually test a hypothesis. Okay. So in this particular case, our hypothesis is that the structural strength of the wire is indeed 200 pounds. Okay. So that's kind of what we have here in step one. And in step two, this was kind of the last thing that we went through before we left, was to form an alternative hypothesis. Okay. So I would say, this is kind of the most important part of this unit here. So it's really kind of crucial that we understand, what the alternative represents and how we form it for any given situation. Okay. So you can think of the alternative hypothesis as the conditions on which, we would say that this test is a failure, or in other words, the conditions that we reject our initial hypothesis. Okay. Because it could be, and this is true a lot in engineering, that, when you test for something, when you try to verify something, the actual values that you measure are going to be different than what you hypothesize it to be. And that's just due to random variance, random uncertainties, just random fluctuations in quality. So, very rarely do you get a situation where your observed, measurements actually match up with what it was hypothesized to be. Okay. And so the idea with the alternative is like, okay, what's the worst case situation in terms of, if we get measurements that don't match our hypothesis, what's the worst case where we would actually just flat out reject our initial hypothesis. Okay. So there are three different types of alternatives that we typically can do in these situations. So we have a right-sided hypothesis, a left-sided, a right-sided alternative, a left-sided alternative, and what's called a two-sided alternative. Okay. And they correspond to, whether our observed value is greater than our hypothesized value, whether our observed value is less than our hypothesized value, or whether, our observed value is just not equal to our hypothesized value. Okay. And we have to choose one of these three, for every experiment that we're going to run, just so that we know the conditions for failure. Okay. So that's one way that you can think of the alternative is, you can think of the alternative as the conditions for failure. Okay. Now, given the situation that we're working with in this example, where we're basically saying that, our wire has to hold at least 200 pounds, right? Let me just put that in here, at least, right? So in other words, our product is going to fail if our structural strength was less than 200 pounds, okay? So that gives us some hints as in terms of, what our alternative should be in this case. And so with that in mind, for this particular example, we're going to choose a left-sided alternative, which states that, if our observed value is less than 200 pounds, then we're going to reject our initial hypothesis and say that, these structural wires are not of good quality enough for us to create our product. Okay. So in other words, this hypothesis or this alternative here, right? This being the left-sided alternative. You can think of this as defining the conditions for failure. Okay. So you want to make sure that, when you're doing these hypothesis testing, for your homework, make sure you choose carefully. And so sometimes the problem will tell you, straight up to use a left-sided alternative, right-sided alternative, two-sided alternative. But, when you're kind of doing this yourself, or if the problem doesn't give it to you, really ask yourself, what is the most appropriate alternative in this case? And really make sure that you choose one that makes sense given the context of the situation. Okay. Okay. All right. So first thing we're going to do today is we're just going to continue right off where we left here. But, I wanted to kind of summarize this and kind of jump right into it. So, when you're testing hypothesis, the first two steps that you have to do, step one, form your initial hypothesis, which is usually some kind of equality statement. Step two, form your alternative and choose one that makes sense given the situation. Okay. All right. Any questions on these steps so far? Okay. All right. So let's go ahead and get to step three. Okay. Step three is to choose something that we call a significance level. Okay. Okay. So significance level, you can draw a lot of comparisons with this with how we define confidence level in the previous chapter, right? Because whenever you're taking real life measurements, real life experiments, there's always going to be some random fluctuations, right? Okay. You can compute things all you want on paper, but until you actually go out and try stuff, there's always going to be some level of variance. Okay. Okay. Because what can happen? So let's take this structural wire example as a case, right? What can happen is that your observed measurements for let's say the tensile strength of this wire is going to be different than what we hypothesize it to be. And so, for this particular experiment, our hypothesized value is that our tensile strength or load limit is 200 pounds, right? But we could have a situation where, maybe let's say that we drew some samples, we measured the tensile strength, right? Maybe we have an observed mean, right? So this is after we've done our experiments. So let's say that we have an observed mean of 197 pounds. Okay. Right. In other words, we get an observation that's less than our hypothesized value. Okay. Now the question is, from this observation, should we reject our initial hypothesis, right? Because technically this satisfies our left-sided alternative, right? Our left-sided alternative says that our observed value is going to be less than our hypothesized value. Okay? Right? Because remember the conditions that we had for the alternative is that if the alternative was satisfied, then we reject our initial hypothesis. So it kind of seems like we should in this case, right? Because the observation that we got from our tests is actually less than the hypothesized value, right? But we always have to take into account that there is going to be some variance, and that's always going to skew your measurements, right? And so when you're deciding whether or not to accept or reject a hypothesis, you have to say, like, okay, our observation is different from our hypothesis, but is this difference significant enough? Okay. Because it could be, right, because we're not testing, we know just intrinsically that every single sample or every single part of the structural wire is always going to be a little bit different, right? What we observe for one structural wire is going to be different than what we observe from the next one, even when they come from the same batch, right? Right. It's just like my commute time, right? Every time I drive to school, it's always takes a slightly different amount of time. And so we have to ask ourselves that, even though this is a mean, right? It's a mean that was taken from a finite amount of observations, right? And so let's just say, for instance, that we got this mean value of 197 from 10 different observations or 10 experiments. Right. So is this enough a difference with our 10 experiments to say that, is this significant enough for us to reject our hypothesis, right? Because it could be, right? One possibility is that, out of those 10 people, out of those 10 samples that we got, maybe they're just 10 bad representations for this, for this wire. And the next 10 that we observe is actually going to have a strength greater than 200. Okay? So since we are doing a finite amount of tests, okay? Since we are doing a finite amount of tests, which is always going to be the case, and so you're never going to have enough time to test out a million different pieces of wire, right? There's just not enough time in the world for that, and probably not enough wire, right? We always have to kind of open ourselves to the possibility that we just had, just to kind of put it very simply, just had very bad luck. Okay? I'll give you another example, right? So, if you take a coin, right, a quarter or so, we just know just by inspection that, you flip a coin, there's a 50% probability that the coin's going to land heads or land tails, right? I guarantee you, or I can't guarantee you, there's a strong possibility where if you flip a coin 10 times, right, it's very likely you're not going to get exactly 5 heads and exactly 5 tails, right? Just because it's all up to random chance, right? So maybe you get 6 heads and 4 tails, maybe 7 tails and 3 heads, right? You could get 10 heads in a row. That's a possibility, right? And so whenever you're doing a finite number of tests to kind of, test a hypothesis, you always have to kind of open up this possibility, okay? And the way that we do that numerically is by specifying a significance value. Okay? So a significance level okay. So significance level is a probability, and so it's a probability that you're going to specify between 0 and 1 that that you're going to set to say that, maybe we have like a 5% chance that these 10 samples were a bad representation. Okay. So the symbol that we use for significance level is alpha, okay? And it's going to be some number between 0 and 1, although you're going to most likely choose a number that's closer to 0, because, we are going to open up the possibility that, we did get bad measurements, but, usually you're going to assign a low probability. Okay. So a very common one, or very common values for significance level is usually 5% or 1%, okay? So a significance value of 0.05, this represents a 5% probability that our measurements were not good representations. But 1% is good as well. Okay. Okay, so your significance level, that's usually something that you're going to set. And so typically, depending on the number of measurements that you're gonna run, you can set your significance level higher or lower. And so if you're running a low number of tests, say like something like 10, maybe your significance level will be something higher, like 5 or 10%. But if you're running a lot of tests, like maybe 100 measurements or 500 measurements, your chance of bad luck is probably going to go down at that point. So you can set your significance level to be lower than that. But it also depends on the variance of your experiment as well. So, if you're not sure what to set for the significance level, 5%, 1%, those are usually good starting points. And then you can kind of see, how that affects your results. Okay. Okay. But significance level is something that you need to set because it's going to affect how we do the next few steps. All right. Any questions on this so far? Okay. All right. So that's step 3. So step 3 is to set your significance level. All right. Step 4. Once you kind of have all these conditions set, step 4 is to actually conduct your measurements or conduct your experiments. Okay. So this is when you actually run your tests, you collect your measurements, and you haven't decided yet if you're going to reject your hypothesis, but this is where you're going to collect your data to do so. Okay. Now, from your measurements, you do need to compute some things. So first thing you're going to compute is the sample mean, right? So you're going to take the value of all your measurements and then just divide by the number of measurements. So that gives you your sample mean. So usually the sample mean is given by your variable with a line over it. All right, so the next thing you're going to compute is the sample variance, right? So remember, we had a formula for that, that we've gone over a few times. So that's given by the simple S squared. And then from the sample variance, you can compute the standard deviation. Okay. So to get the standard deviation, we're just going to take the square root of the sample variance. It's pretty straightforward. All right, and the last thing you're going to take note of, well, you probably already know this just by computing the sample mean and sample variance, but you need to make note of the number of measurements or the number of experiments that you're going to run, and you're going to save that as n. Okay, good. All right, so after you run your experiments, now you're gonna do some calculations to see, if if your measurements are enough to either justify your hypothesis or reject it. Okay. Okay, so step 5 is to compute what's called your t-value, right? So your t-value here is going to be basically a normalized difference. So you're going to take basically the difference between your sample mean and the hypothesized value, and you're going to normalize it based on the variance and based on the number of tests that you've done. Okay. Okay. All right, so the formula for the t-value is given by the following. So we have t is equal to, so in the numerator for the t-value here, we have the difference between the sample mean and the hypothesized value. Okay, so we have difference between mu bar minus mu. Okay. Right, so whatever you obtain from the measurements, subtract from that the hypothesized value. And then you're going to divide this by a quotient. And so on the bottom, you're going to have the standard deviation divided by square root of the number of measurements. All right, so this will give you a normalized difference. Okay. And then depending on the variance of your data, depending on the number of measurements that you have, this will kind of help normalize that for you. Okay. So for this example, let's continue on with our structural wire. So for this example, let's say that we have n is equal to 25 tests. Okay. We already have our sample mean, so our sample mean is 197 pounds. Okay. Let's say our sample variance here is 36 pounds square. And so we take the square root of that. The standard deviation is 6 pounds. Okay. Okay, so if we plug all those values in, we get a normalized t value, right? So we're going to get a negative number here. And so, you get whenever your observed value is less than the hypothesized value, your t is going to be less than that. Okay. Okay. So we get a t value of minus 2.5. Okay. So this t value here is going to help us to determine whether our difference is significant enough to reject our hypothesis. Okay, which is what we're going to do in the next step. But that was step 5 there. Any questions on the process so far? Yeah.
What's the normalized difference?
So normalized difference just means that it's we normalize out the units. And so normally when you take just say mu bar minus mu, that gives you something in units of pounds in this case. And so we divide it by the standard deviation. So that'll get rid of the pounds. And then we also scale it based on the number of measurements. So when I say normalize, it just means we scale it just to make it make it easier to interpret. Right, any other questions on this? Okay. All right, so that's step 5. All right, step 6 in the process is we are going to compare our t value with a with the probability density function of a random variable. Okay. And so depending on this comparison, so depending on if our comparison is good or not, that's going to tell us whether or not we should reject our hypothesis. Okay. Okay. Now, the choice of random variable that you choose is going to depend on the nature of your measurements, right? So usually there's two options for this. Okay, so the first option, which is a little bit less common, so usually you're going to use this first option for for fairly simple cases like the ruler case that we did last time. And so the first case here is going to be a Gaussian random variable or a normal random variable. Okay. And so for a Gaussian random variable, this is going to be table A8 in the textbook. Okay. So for a Gaussian random variable, these are for cases when you know the variance beforehand, so before even conducting any test. Okay. And so if you think of, if you think back to the example we did last week where we were measuring, we were measuring the length of a phone using a ruler, right? That ruler has a fixed precision. It was a very simple kind of case. And so in that case, we already knew the variance before. Okay. But this is usually pretty rare for most practical cases. Okay. Okay, so the second case, which is the one we're going to use for this example, is a t distribution. Okay, so this is table A9 in the textbook. And so you're going to use a t distribution for cases when you are measuring the variance. Okay. Which is exactly the case that we did here. So we computed our sample variance, and so we're going to use our t distribution. Okay. Okay. All right, so, but no matter which case that you're going to use, the calculation is very similar, okay? Okay, so first thing you're going to do, very similar to how we did our confidence interval testing, is we're going to compute a quantity known as f of c. Right? So f of c in this case is just going to be equal to our significance level. Okay. This is true for a left-sided alternative. Okay. You're going to see we use slightly different expressions for a right-sided alternative and a two-sided alternative, but we'll do examples of those later. Okay. All right. And then what you're also going to compute, just like in our confidence intervals, you're going to compute the number of degrees of freedom. Okay. Where degrees of freedom, remember, are just n, it's just n minus 1, so the number of experiments that you ran minus 1. Okay. All right. And then what you're going to do, just like we did in confidence intervals, is we're going to take both of these informations and then we're going to look up in table A9. Okay. We're going to look up in table A9 for the value of C that corresponds to these two, these two calculations here. Okay. All right. And so if you look at table A9, I'll draw kind of a very quick version of this again. Okay. All right. So the first column in table A9 is going to be f of C, right? And so this might be, 0.01, 0.02, ... 0.05. Okay. So you're going to go to the row for f of C that corresponds to our significance value. Okay. And so for this problem, our significance value is 0.05. So we're going to go to that row just like that. Okay. And then the columns, each of the columns are going to correspond to different numbers of degrees of freedom. Right. So we have 1, 2, 3, 4, ... 24, 25. Right? Okay, and so for this particular problem, we have 25 measurements. That means our degrees of freedom is 24. Okay, that means we're going to go to that column there. And then just whatever we see in this entry right here, that's going to give us our value for C. Okay. Okay. And so if you look up the table with those statistics there, then what we get is a value of C of minus 1.71. Okay. All right. Any questions on this part here? Okay. All right. So now that we have our value of C, we have our value of T here. We are ready. We have all the information we need to reject or accept our hypothesis. Okay. So step 7 is we're going to compare our T value to the C value. Okay. And so depending on the relative value of T versus C, then this is going to tell us whether we should accept or reject our hypothesis. Okay. And so let's talk a bit more about what the C value represents. So the C value represents the maximum normalized difference between our mean and our hypothesized value that where we can still accept our hypothesis. Okay. Right, and so with the C value of minus 1.71, that tells us that our normalized difference can't be worse than minus 1.71 if we want to accept our hypothesis. Okay. So remember, we're doing a left-sided hypothesis, and so you know, our criteria for rejection is that our normalized difference is less than that. Okay. So if we compare our t value versus c, right? For this problem, we got a t value of minus 2.5, and our c value that we looked up from the table is minus 1.71. Okay. So in this case, you know, our t value is less than our c value, right? So that means the difference that we're observing is indeed significant enough for us to reject our hypothesis. And so what we say is that, you know, in this case, we're going to reject our hypothesis, and we're going to do so with 95% certainty, right? Because, you know, we chose a significant value of 0.055%. And so there's basically only a 5% chance that our observations were bad. And so based on our observation, there's a 95% chance that indeed we can reject our hypothesis. Okay. It's very hard to get 100%. Just because, you know, remember, you're taking a finite number of measurements. Even if you take 1,000 measurements, there's still a non-zero possibility that those 1,000 measurements were just really bad luck. And so you always have to kind of, you know, temper your statement with a certain probability. Okay. Okay. So it's a long process, and so there's a lot of things to do. But the actual amount of calculation that you do is actually quite small. So, you know, a lot of this process is just kind of really understanding conceptually what you're doing in each step and what each of these values kind of represent. But, you know, the most calculations that you're going to do probably is going to be in step 4, where you run the experiments and compute your sample mean, your sample variance. Once you have that information, then everything else, you know, very simple calculations is just, you know, kind of understanding what's going on. And like I mentioned earlier today, that, you know, with these kind of stuff, with the probability and statistics, you kind of have to talk your way through it a few times before it really starts to kind of sink in terms of, you know, okay, you know, this makes sense why we're doing this. Okay. Okay. Any questions on this? Okay. All right. So let's do another example. Let's do a let's see. So that was a left-sided alternative. Let's do it. Let's do a right-sided alternative. Okay. Okay. So, that was the first example that we did. So, we kind of went through each of those steps very, very carefully. From here on out, we're going to go a little bit faster just because, we've seen them before. Okay. Just that I want to mainly show you the differences of what happens when you do a right-sided alternative and a two-sided alternative. Okay. So let's do a very, very simple case. So let's test the hypothesis that the value of a random variable is equal to 24. Okay. So just a pure math example. So, we have a random variable, we can draw samples from it, and, we want to hypothesize that the value of this is equal to 24. Okay. Okay, so that's our hypothesis. So let's go through each of the 7 steps again, and just kind of walk our way through it. Right. So our hypothesis in this case. We're going to call our variable x here. Our hypothesis is that x is going to be equal to 24. Okay, step 2. Step 2, we're going to define the alternative hypothesis. And for a right-sided alternative, our alternative in this case is that the observed value for x is actually going to be greater than 24. Okay. Step 3 is we're going to choose our significance level. Okay. And so in this case, we're going to choose, just kind of somewhat arbitrarily, we're going to choose a significance level of 5%. We're not going to take that many tests in this case. And so, the significance level of 5% usually is pretty reasonable here. Okay. Okay. Now, for this one, we're going to deviate a little bit because usually step 4, this is when you collect your measurements. Okay. But we're going to modify the objective of this problem a little bit. Okay. So in this problem, we have a right-sided alternative. Right? And so instead of collecting measurements, let's instead ask the question of, what's the maximum value of our observed mean that we can have before we reject our hypothesis. Okay. So we're basically asking the question, if we were to run some tests, what's the maximum value of that mean that we can have before we reject our hypothesis, okay? Because with the right-sided alternative, a right-sided alternative basically means that if we observe a value that's greater than our hypothesized value, then that gives us, grounds to, reject it if that difference is significant, okay? Okay, so to do this, we're going to need to make some assumptions. And so we are going to have to assume that we know the number of samples. So let's say that, we're going to perform 10 tests. 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 10 tests And because this is a Gaussian random variable, we can assume that we know the variance beforehand. All right, so we're going to assume that we know the variance. In this case is going to be 9. Okay. And so this tells us that our standard deviation, which is just the square root of the variance, is going to be equal to. Okay. But you can see that the way that we ask the question is slightly different. We're still going to use the same formulas. It's just that, we're going to modify our approach a little bit. So we're going to look up the table early and use that to kind of pre-compute our t values. We'll see. Okay. So this way of thinking, or this kind of approach to hypothesis testing, this is actually very similar to the approach that's taken in quality control. Okay. And so if you work for a company that's manufacturing a lot of products, one thing that they're always doing is they're monitoring their product production line for quality, just to make sure that the products that they put out, that they sell, meet some kind of minimum standards, so that they can, so that the product actually does what it says it's going to do. Okay. So one question that you're always asking yourself in quality control is, as we're producing this this product, and we're getting all of these measurements for the quality of the project, what's the worst that our quality can be before we have to stop production and maybe, find something that may be wrong with our process. Okay. So this is a way to kind of do quality control on the fly, right? Because even when you're producing products, right, there's always going to be some fluctuations and variance in the quality, and you want to ask yourself, when is this when is this difference significant enough for us to actually go in and adjust? Okay, so this way of thinking is very common in quality control. Okay. All right, so our next step here is to compute our t value. Okay. But of course, because we don't have measurements, we can't explicitly compute our t value, but we can at least come up with an expression for our t value. Okay, so our t value in this case, t is equal to, let's see, observed quantity minus the hypothesized value divided by the standard deviation divided by the square root of the number of measurements. Okay. So that's our standard formula for t value. Okay. Normally, what we would do is that, if we ran experiments, we'd have everything we need to plug in on the right-hand side of this equation, and we can compute a value. Okay. But since we haven't run any experiments yet, we don't know what this one's going to be. And so what we're actually going to do is we're going to take this expression and solve for x bar. Okay. Because what we can do, right? Because we're looking up the threshold anyways, that we can look up in our tables what the value of t should be. Right? And in this case, because we know the variance beforehand, we can look in table A8. Right? And so from there, we can compute x bar from this. Okay. Okay, so let's go ahead and solve this for x bar. And so if we solve this for x bar, we get x bar is equal to t multiplied by sigma over square root of n plus x, our hypothesized value. Okay. Okay. And so based on the standard deviation, based on the number of measurements that we have, square root of n, And based on our hypothesized value, we can compute, the maximum of what X bar can be before we start to reject hypothesis. Okay. And of course, the linchpin in all this is our value of T that we need to look up in the table. So that's kind of what we're going to do in the next. Okay. All right. Any questions on this? Okay. All right. So let's look up the value for T. So that's going to be step 6. Look up the value for T. Okay. So just like we did in the previous example, we're going to compute f of c. Okay. So remember, c and t are of the same family, right? So we're going to compute f of c, and we're going to compute our degrees of freedom. Okay. So our f of c, remember in the previous example, this was just given by our significance level, which is equal to 0.05. Okay. And our degrees of freedom in this case is n minus 1, which is 9. Okay. Okay. And so we look this up in the table, right? So we go to table A8 in this case, and we look at the column for f of c, 0.05. We look at the column for degrees of freedom of 9. And what we get is a c value, which is equal to our t value in this case, of minus, where'd it go? Minus 1.645. Okay. So now what we can do is we can plug this in and we can compute a value for X bar. Okay. So we plug in this. All right. We get X bar is equal to minus 1.645 multiplied by our standard deviation. Standard deviation in this case is 3. Okay. Because we had a variance of 9. Right. We're going to take the square root of the number of samples, so square root of 10 plus 24, which is our hypothesized value. Okay. All right, so if we punch these into a calculator, I apologize, I don't have I don't have it right in front of me. Okay. We do that again, square root of 10. Oops. Okay, we get an X bar of 22.44. Okay. So this is telling us, right? So because we have a right-sided alternative, this is telling us that if our observed value is greater than 22.44, then we should reject our hypothesis. All right. So we got this result here, but we should ask ourselves, does this actually make sense, right? So if we think back to the problem, right? our hypothesized value for X here was 24. Right? And so according to our calculations here, so if we observe something that's greater than 22.44, then we reject our hypothesis, right? What if we observe, what if we just so happen to observe that our mean value was 24? Right? So in other words, we make an observation that our observed value is exactly the same as our hypothesized value, right? So that should be good, right? So the fact that we observe something that's exactly the same as our hypothesis means that that should be what we do, right? But according to alternative, since 24 is greater than 22.44, right? According to that metric, we should reject our hypothesis, right? So something's not adding up, right? So this threshold here doesn't really make sense because we chose a right-sided alternative, but the threshold that we got was actually less than our hypothesized value. Okay. So something went wrong because this result here doesn't really quite make sense. And so if we have a right-sided alternative, then our threshold should be to the right of our hypothesized value, not to the left, right? And so something went wrong. Right? And so something did go wrong, and it had to do with the value of C that we looked up in the table, right? And so because our value for C or T was negative, then that led to a threshold value that's less than our hypothesized value, which led to this kind of nonsensical result, right? Okay, so what do we do in this case, right? So what do we do in situations like this where we have a right-sided alternative, but we get a negative T value or negative C value, okay? So there's an easy fix for this. And so the fix has to do with how we look up entries in the table, okay? Okay. And so when you have a right-sided alternative, you can't just look up f of C is equal to alpha, right? So you have to make an adjustment here, okay? And the adjustment has to do with the fact of how distribution functions are defined, okay? So I'll kind of just for the sake of time, I'll kind of skip kind of the explanation. Well, I'll mention a little bit of this, but remember distribution functions are defined as the probability that your observations are less than a certain threshold, right? And so it doesn't go the other way. And so when you have a right-sided alternative, you have to modify this. And so instead of doing this, so for right-sided alternative problems, for right-sided alternative problems, we're going to use an alternative expression for f of C. Okay? And so in these cases, we're going to have f of C not equal to alpha. We're going to have f of C is equal to 1 minus alpha instead. All right, so this will take us kind of to the other side of the distribution, which will give us a positive number for T, which will kind of make all of these things kind of make sense, okay? All right, and so if we run through those calculations really quickly, 1 minus alpha here is going to be 0.95. We can look up in the table for these number of degrees of freedom. What we get is a C value of positive 1.645. Okay. Okay. All right, and so we run through the same calculations, we plug it in, we get the threshold value for X bar to be 25.56. Okay. So this makes a lot more sense because this tells us that, if we get an observed value that's greater than 25.56, then we're going to reject our hypothesis. Okay. So that makes a lot more sense for a right-sided alternative. So just be careful when you're looking up the value for f of c, and you make sure you use the appropriate one depending on if you're doing a left-sided alternative or a right-sided alternative. Okay. Okay. Any questions on how we did any of that there? Okay. Right, and so this trick actually you can kind of use it both ways too, because sometimes when you look up in the table, your value for f of c may not be in the table, but you can take advantage of the fact that f of c is, your distributions are symmetric. Because sometimes the row for f of c that you're looking up may not be in the table, but you can look up the reciprocal value and then use that and just multiply by -1. Okay. And what do I mean by this? So let's say that you're doing a left-sided alternative problem. We're using a alpha value of 0.01. Okay. And so if you try to look this up in the table, right, you may find that there's no row for f of c is equal to 0.01. Okay. And so, at that point, you may look at the problem, you may think like, oh, I'm stuck. I can't look up a value for C. I can't compute my, confidence intervals. I can't compute, my rejection region and all that stuff. Okay. But if you look at the table, maybe they don't have a row for 0.01, but they may have a row for 0.99. Okay. So you can actually use this value and just know that, the distributions are symmetric on both sides. The only difference is a change in sign. Okay. So what you can do is you can obtain C from this entry here. Okay. But because you're looking at the other side of the table, you have to multiply by -1 in order to get the appropriate C value for 0.01. Okay. So sometimes you may have to do this. So, just if there's no row for your significance level, just take the other side, multiply by -1. Yeah, you'll be good for it. Okay. Okay. Any questions on this? Okay, so last thing I want to do today before we head out, we're not going to do another full example. I do want to tell you guys what you have to do for a two-sided alternative. Okay. So for a two-sided alternative, you're going to check thresholds both less than and greater than your hypothesized value. Okay. And so in some sense, when you have a two-sided alternative, you're going to do basically the same thing twice. And so you're going to do a left-sided alternative and a right-sided alternative. Okay. The only difference is that, oh, sorry about that. Did the mic cut off for a second? Okay. Yeah, so if the observed value was greater than 25.56 for our right-sided alternative, that's when we reject our hypothesis. Yeah. Yeah, so that's for a right-sided alternative. So you want to make sure that when you're doing a right-sided alternative, your threshold is actually above your hypothesized value. Yeah. Okay, so for a two-sided alternative, you're going to check both the threshold less than and greater than. But you want to make sure that you don't over assign your significance level. Okay. Okay. And so when you're doing a two-sided alternative, you're going to assign half of your significance less than your hypothesized value and half of the significance greater than the hypothesized value. Okay. All right. So for the left side, normally we have f of c is equal to alpha. Okay. But when you're doing a two-sided alternative, you're going to do f of c is equal to 1/2 alpha. Okay. And then you're going to compute all of your C values and stuff from that way. Okay. And then on the right side, okay, your f of C is going to be 1 minus 1/2 alpha. Okay. Instead of 1 minus full alpha. Okay. Right. And then besides that, you're just going to run through the problem the same way twice. And so for both cases, you're going to compute a T value. And then from there, you can either compute a threshold, or if you already have your measurements, you can use that T value to determine if you're going to accept or reject your hypothesis. Okay. All right. So for two-sided alternatives, it's not worth it to do another full example. Just know that you have to do it twice. It's just that for each one, you're going to do a half, um, you know, half significance. All right. Any final questions on this before we wrap it up for the week? Okay. All right. So that's it for today. And so when we come back on Tuesday, I do want to do one last example with hypothesis testing just to kind of nail down the whole process. We didn't really have enough time for today. And then we're going to cover our final topic for the semester on Tuesday, which is linear regression. Okay. All right. So thank you guys for coming today. Hope you guys have a good rest of your day. Hope you guys have a good weekend. And I will see you guys next week. Thanks, guys.
Yeah, should I go up to the left side?
Yes.
I didn't pop it on my notes, I just wanted to get a picture.
Tell me when to stop.
Um. Right there.
Here?
Is that the left side?
Yeah, this was the left.
No, I got that.
Okay.
Isn't that stuff from, down?
Oh, this one, this part right here.
Yeah.
Okay. Just like that. Down to one.
Oh, wait, is this the right side?
Yeah,
Okay.
so this whole example was right side, but we kind of, I showed you that, if you do this as if it were left side, you get an answer that doesn't make sense, so.
Oh, I'm
Yeah.
talking about the part before this one.
Oh, okay,
Sorry, I don't think we.
right here,
No, one more down, just a little more down. And one more down.
Yeah.
Yeah, one more down.
yeah,
Sorry.
no worries, no worries.
Can you go down? Yes. Can you go down? Okay. Got it. Okay, thank you so much.
Yeah.
Did you pass back the exam?
I did, oh shoot, I didn't bring them today.
Uh,
You have time right now? Real quick?
Yeah.
Okay, let's go to my office, we can pick it up for my next class. So let me see, chat.